Hi there. So in the last video we talked about solving a linear first order differential equation. And in fact, the one we looked at looked like this. Okay, we solved this differential equation, right? And how did we do it? Well, we got the y's on one side of the equal sign and the other terms on the other side of the equal sign, and then we anti-differentiated. Now what I want to point out to you is that we could do this in a little bit more of a general sense, right? So we can do this even if a is not a constant, even if this is a function. So what I want us to do here is consider the following differential equation. This is a linear first order homogeneous differential equation. Homogeneous because the right-hand side is 0. Okay. Now, how would we solve this? Well, if you go make sure you go look back at that other video and just follow the same steps that we did for the other one. Just do the same things here, and we can get a solution, provided that we can anti-differentiate p of x. All right. So, how are we going to do this? Well, the same thing we did before. We isolated the y's on one side. So I'm going to subtract p of x times y from both sides. Divide both sides by y. Right? And then what do? We anti-differentiate. And if you recall from the other video, what we get over here is the log of absolute value y. So let's pull that up here. When I anti-differentiate this. When I anti-differentiate this, well, I'm just going to have the antiderivative. So let me just write that down. All right. And then we continue solving for y. We got rid of the primes. Now we just solve for y by taking the exponential function of each side. Right? So we end up with y equals e to the negative integral of p of x dx. And if you recall, a constant comes out front here. Okay? So we can find the solution, and it's pretty quick. This is how we get it. And as long as we can find the antiderivative for p of x, we can write this down explicitly. Even if you can't find the antiderivative, well, you could write it down this way and say that, you know, whatever the antiderivative is, that's what goes up here, right? So you can, sometimes we might leave the answer using an integral symbol. Okay? So what I want to do in this video is go a little bit further from here and look at differential equations that aren't homogeneous, where we don't have a 0 on the right-hand side. Okay? So what would we do there? Let's take a look. Let's write one of these down. So what we're looking at is differential equations of the form like this. This is what we're going to focus on in this video. So let me, here's the strategy. What we're going to do to solve this, and it isn't obvious that this will work, but we'll see why it will work once we go through it, is we're first going to solve the homogeneous equation. Okay? And from that, we're going to get what's called the complementary solution. Okay? So from this equation, we're going to construct the homogeneous equation. What is that? That's what you get when you just replace f of x with 0. The book calls this the complementary equation. And we know how to solve this. That's what we just did up here, right? So we know how to find the solution. All right? So when you get the solution from this, which will be that, right? Well, we're going to call that y1. Okay? And this is what we're going to call the homogeneous solution. Or the complementary solution. And so you'll see in some books they write a subscript C here, C for complementary. Okay, so we're going to get that. Okay, now what do we do once we get that? Because that's not the differential equation we want to solve. This is the one we want to solve. Well, here's the trick. And the trick is actually called variation of parameters. And that's something we're going to talk about in more detail in a later chapter. So it's not so important that we know that that's what it's called right now. But the method we're using is called variation of parameters. Oops, parameters. Okay, and what do we do here? Well, we're going to take our complementary solution, our homogeneous solution, and we're going to multiply it by another function. Okay, so consider this new function. We're going to take our complementary solution and we're going to multiply it by a new function u. Okay, so now we have some new function. Now, what we're going to do is we're going to see if we can fit this back into our differential equation and just see what comes out. All right? So let's try this. So if I'm going to plug it back into this differential equation, I need to find what y prime is. Okay, so let's compute y prime. Well, I use the product rule here, right? Because this is a product. So I get this. Okay? So in place of y prime up here, I'm going to put this guy. And in place of y, I'm going to put this guy. So let's write that all out, okay? So what we get here, this is what we get in place of y prime. In place of y, I'm putting this. And so this is my differential equation. Okay. Now, let's simplify this a little bit. Let's factor out some terms. What I'm going to do, actually, is I'm going to factor out the u over here. Okay? Let's see what happens. Now see, pause the video and take a look at this. See if you can see something that we can use. Something simplifies very nicely here. Look back at the work and see if you can see what we can use here. Okay? So hopefully you paused that video and maybe you figured it out. You should have realized that this guy right here, this expression, is something we've seen before. This is the differential equation with the complementary solution plugged in. All right? So it's this differential equation, right, but with y1 plugged in place of y. Right? But what happens when we plug y1 in place of y? Well, y1 is the thing that when you plug it in place of y, it's the solution to this. Right? And what's this? This is equal to 0. So if I plug y1 in place of y, this part becomes 0. That's what y1 is. That's what the complementary solution is. It's the thing that makes that 0. So what we're saying here is that this is just 0. Okay? So look at how this simplifies. All that goes away, right? So I just get u prime y1 equals f of x. That is fantastic. And we've already found y prime. We've already solved that complementary solution, so we know what function this is. So let's just divide both sides by y1. And what do we get? y1 is a function of x, so I'll emphasize that by putting of x over here. We get this new differential equation. We knew what f of x was because that was given to us at the beginning of the problem. We'll know what the right-hand side of our differential equation is. We're going to solve the complementary equation and find y1, so we'll know what this is. So now we know what this is. This is completely known to us. So what are we going to do? To find u, we will just anti-differentiate both sides. right? So u just ends up being the antiderivative of this stuff, which hopefully we'll be able to do because we know what functions these are. Okay? Now what do we do with that? Well, now we're pretty much there, because if you remember, y is equal to the solution that we want. Y is equal to u times y1. So all I have to do is take this thing and multiply it by y1, and that's our solution. Our solution is, what did I say? U times y1, right? But u is just this. It's the integral multiplied by y1 of x, right? So that's how we're going to solve this differential equation. It's a trick. It's not obvious that, you know, that it would work at the beginning, but we can see that it pans out. And the key to that working was because it makes this term 0 over here. Okay, so let's do this with an example so we can see this working, you know, with particular functions in place of these variables. Okay, so the example that I want to look at is this one. Okay, so my p of x is tan x, and my f of x is cosine x. I'm going to solve this. So what was the first step? First step was solve the complementary equation. All right. Or homogeneous equation. I guess I'm calling it complementary now. All right, so we're going to solve this. So how do we do it? We get the y's on one side. I subtract, divide by y, right? I get y prime over y equals negative tan x when I use a little bit of algebra here. Anti-differentiate both sides. You get the natural log of y equals, what's the antiderivative of tan x? It is, what is it? It's natural log of cosine, right? Natural log of cosine x, right? And I think the negative sign comes for free there, because when you differentiate this, the negative comes out, right? Now you get a plus some arbitrary constant, right, when you anti-differentiate. Now, well, I'll keep it here for now. I'm going to say later that we can just assume this thing is 0, and you'll see why. All right. Actually, let's go ahead and do that. Let's assume that this constant is 0, and I'll explain why we can do that in the end. Okay. So we're going to solve this for y. So we'll take the exponential function of both sides. So you take the exponential function of this, you just get cosine x, right? So all right, if that constant was different, we might get a different constant out front over here, okay? But we'll see that that doesn't really matter, and that's because of the next step, all right? The next step is to okay, let me go up and correct this. So we were finding the complementary solution, right? That's what we called y1. So let me put a 1 here in place of all the y's, right? Now the real solution, we're going to suppose that y is equal to u times y1, right? So the real solution we're calling y. So what we said was, so let's go ahead and plug this in. So this is going to be some function u times cosine x. Okay, let me just hop right in here because I forgot to explain why we can let that constant be 0. Okay, so let me go in and interrupt what we were doing. We said that this constant here can be set, we can assume that it's 0. Why is that? Well, because when we moved from this step to this step, how did we do that? We took the exponential function of both sides, right? And now, because of properties of logarithms, this is the exponential function of log of cosine x and plus c, but that's the same thing as multiplying by e to the c. And this is just a constant, right? So this thing just becomes, I can just let this be a constant a, right? So this is just a times this thing, and here the log and the exponential function cancel out, so I just get cosine x. And the absolute value, as I explained in the last video, can be absorbed into that constant, right? So I can get rid of the absolute value just by making this constant plus or minus, right? Now, so you might say, well, we have a constant a over here, right? Well, look at the next step. We let y equal u times y1. So why should I bother writing a constant a here when I could just assume that that a is a part of u, right? So u is being multiplied by y1, so let's just assume that the constant is in u instead. So we can assume that this constant is just 1. And that's why we can assume that this constant is 0, because that's what makes that constant equal to 1. Okay? So what happens here? What did we do before? We computed y prime. So we get u prime cosine x minus u sine x, right? Plug that in to the original differential equation. And what do you get? You get now, it was tan x times y, so now it's u times y 1. It's u times cosine x, right? And the right-hand side is cosine x. Right? Now, what did we do before? We factored out the u, right? Do I want a minus here or a plus? Let me put a plus here. And so that's a minus sine x plus tan x times cosine x. Okay. Now, check this out. Do a little, just use your trig. What is this equal to? Yeah, it's 0, right? That just becomes 0. We knew that was going to happen. In fact, I didn't have to go through all these steps, because what we showed before was that we're just going to get to here, right? We know we're just going to get to here, so I could have just skipped to this step. But what I'm doing is I'm showing you step by step that to convince you that yes, that's going to happen. All right, so let's go ahead and wipe that out, because that's all 0. So this stuff is all gone, right? So we get this, divide both sides by cosine, and we get this. And that is, like I said, that's exactly just this, right? F of x, the right-hand side of our differential equation, was cosine, and y1 of x was, what did we get? Cosine. And when you divide them, you get 1. So we could have just jumped right to here, right? But just in case you didn't believe that computation we did earlier was true, here it is worked out in the details of this specific problem, okay? So there's u prime. We can solve this for u. So what do? We just anti-differentiate. If I anti-differentiate this, what do I get? I get x plus a constant, right? Now I'm not done, because what I'm trying to find is not u, I'm trying to find y, right? So recall, y was equal to u times y1. Okay, well, we just found u, so plug that in place of u. And we knew what y1 was. y1 was cosine x. And there we have our general solution. So we found the complementary solution, and then we use the method of variation of parameters, which means to multiply that complementary solution by this, plugged it back into the differential equation, and we found the general solution. Okay? All right. Now, I just wanted to point out that in your book, they actually they have a little part of section 2.1 where they actually step you through this. This is exactly the steps that we made. All right, so please take a look at that in the book. This is the method of variation parameters for solving this type of differential equation here, right? So these are exactly the steps that we went through. Some of these things might look a little bit different because they've jumped ahead to certain parts, but you should be able to identify that this is exactly where we got to. And we did every one of these steps in finding the solution. Okay, so that's all I had for you in this video, and we finished section 2.1, so I will see you with the material for section 2.2 when we get there.